Hello everyone, welcome to EC TechNest. In today's series of Verilog and digital design, we'll be looking forward with encoder, decoder, and priority encoder. Decoder. A decoder is a combinational circuit that converts an n-bit binary input into a maximum of 2n unique output lines. Only one output line is asserted. It means it is active at any given time based on the binary value of the input. Real world use cases. You use it in memory addressing. When a CPU wants to read from a specific RAM location, it sends a binary address to a decoder. The decoder activates exactly one row of the memory cell corresponding to that address. We'll see how it works, okay? See, this is a 3:8 decoder. It has 3 inputs and gives 8 output lines. As we said, it's a real world example is memory selection. If you have 8 different memory chips, the CPU sends a 3-bit code, that is 011, to the decoder. The decoder then turns on chip select wire for the third chip specifically. It means if you give a input with 3-bit, the chip select will decide it will go to the third chip based on this code, leaving the others off. This is a Verilog code for a 3:8 decoder. You have a 3-bit binary input and the output is of 8-bit. Always at all cases, we have put a case here for binary input. Based on this input, what output it will get. So change in the input will result in a different output. 3 dash binary 000. So if you have 3 dash binary 000, your output will be 0001. So the first bit will become 1. Similarly for 001, you will have the shift from the 0th bit to the first bit. Similar way, you will see the increment here. We'll set a default case in if any of the input is not given in the test bench. The default case will be 0. It means all the 8 bits will return 0. Encoders. An encoder does the exact opposite of a decoder. There you had n inputs getting converted to 8 outputs. Here you will have the opposite of it. It takes 2n or fewer input lines and compresses them into an n-bit binary code. Real world use case. A keyboard matrix. When you press a key on a calculator, the hardware detects which specific wire was pressed and encodes it into a binary code. The processor can understand it as a number 5. We'll see how this works now. This is your 8:3 binary encoder. Here you have 8 inputs and based on that we'll get a 3-bit binary output. This is what is written here. Let us see how it works now. Considering the same whatever we saw for a decoder, here you have a 8-bit input and a 3-bit output. Case is D. It means for the case whatever the inputs are changing, we'll get the desired output. Let us see. For the first out case, like you have a 8-bit 00001, and for that you will get y equals 3 dash b000. That means button 0 is pressed. In a similar way, if you have 1 0 at this, it will become 001. You will get button 1. And even here we have a default case where we'll be going with 3 dash b000. But in this thing, do you see any problem? Okay, let me consider this simple case. Here, what happens is this is a kind of a tricky thing. You need to carefully listen to it. What if I press 5 and 6 together? Here, only one button is getting pressed. It's okay. But suddenly I decide, no, I want to have some fun. I'll press 5 and 6 together. That time, there becomes a latching. It means don't get any output, right? So to solve this in the modern electronics, we do not use encoder. We use priority encoder. See, the same example is given. In the code above, if you accidentally press button 2 and button 7 at the same time, the case statement will hit the default or behave unpredictably. Because the input A-B 10001000 doesn't match any specific pattern. As we see, that pattern is not present here. This is why priority encoders are used in almost all real-world applications. They are designed to choose the highest number if multiple buttons are jammed down simultaneously. We'll see the example here. An 8 is to through encoder take 8 inputs and it will give 3-bit binary code. We use a priority version here because in the real world, two signals might arrive at the same time. Correct. The priority logic ensures the highest indexed input wins. To understand it in a still more easier way, let us think that in the real world example where this will be used. For an example, you are going into an elevator. So you have multiple people coming inside the elevator. Some might press suddenly 2. At the same time, you also might press 5. That means the other person wants to go to the second floor, but you want to go to the fifth floor. How will the elevator know that where should I go first? So we'll give priority. Whoever has pressed first, the controller encoder needs a rule to decide which floor number to register first. So what it will do, this thing is very simple. Okay, the code might look very big for you, but the thing is it will give priority. So the highest bit, maybe the 7th bit, it will get the first priority. See, if the first button is pressed, means request 7, the binary output will have the highest priority. It means 111 you will get. Else if next highest priority, next highest priority, like this till 0. You might feel the code is a bit lengthy. What, should I write this much? So we'll also see how you can write it in a much easier way. You have a module priority encoder. As we know, the same thing we are taking 8-bit input and a 3-bit output. What here we are going to do is we are using a nested conditional operator. We might have discussed this in our previous videos. That means based on this condition, if this condition is 1, this will be our input, or else it is a 0. Since we do not need 0 at these cases, we just left it empty. Default it will be 0 itself. So if our 7th bit is 1, it gets the highest priority. That means 3-B11 is the output. If D6 is 0, that means 6th bit is of the input line is 0. 3-B110 will be output. Only for the last condition, we give both the options. If the last bit is 1, it will return 3-B001. If it is 0, we will get 3-B000. Valid bit is true if any bit in the input vector is 1. It means assign valid /D. It checks if all the input D is valid. Module decoder 3:8 data flow model. Here what we are going to do is based on the inputs, we'll give them the order. See here, how will you know in a simple way? See, if I'm getting a 3-bit input, right, and 8-bit output, I want to know. This is for decoder I'm talking about, not the encoder. This is a decoder. How you can write a decoder using a different method. I have my output here, and I'll tell if when I give my 3-bit input, if all the conditions are 1, I'll get 1. Or else, for a case, let us see like that. Here, if it was 1, 1, and 1, the last bit would not be 0, right? So it would be this. By 7 would come as our output. Only if it is 1, 1, 0. Here you have 1, 1. What will happen if here we do not use this not? This will also become 1. So what we have done is wherever there is 0, we have taken a negation, or we have put the negative symbol. So what happens is only if this type of symbol comes, then you'll get this as output. So we use this method for the decoding part. Instead of writing that lengthy code, we have used this method. But I feel that this is a much easier code to write compared to whatever we saw there. That would be a very bit complex because you need to remember where to put this negation, not put it. So I would say avoid it. The other method that we discuss here, 1 minute. This is a better way of writing the code using a case statement. Thank you. If you have any doubts, feel free to put it in the comment section.